All right. So we have one last portion to talk about with ternary phase diagrams, and it involves a peritectic reaction as well. So the first thing I want to start us off with is, again, going back to this binary system that we talked about with these two compositions X and Y. So I want you to think about composition Y and what happens to the component beta below the peritectic temperature. So take a second to think about this. We talked about this in a previous lecture, so see if you can remember what happens to beta below the peritectic temperature, and then we'll come back and talk about it. All right, so if you'll recall from the previous lecture, this composition Y, we saw that at temperatures above the peritectic, in this region, we form beta, just like we would over here at X. But when we drop below the peritectic temperature, we create AB. That's our peritectic reaction. And so beta has to be consumed to produce that. And so in the case of the composition X, liquid plus beta completely is consumed to create AB. But at this point, we have some beta left over. So if we're at this composition, we see that we have AB plus some beta. So beta is consumed, but not completely. And so that's where we get the partial or partially resorbed terminology here. So this is what we're going to look at, and this is what we're going to look at in a ternary system now, because this is sort of the last component we haven't talked about. All right, so this composition B here, in this different phase diagram that we're looking at, goes through a peritectic reaction, and it does so at 1470. So let me just show that that's the case. So we're at a composition. We're inside the compatibility triangle here. So again, if we draw all the compatibility triangles, we'll see that the composition B is within this compatibility triangle. And that invariant point associated with those three reactions is over here, outside of its compatibility triangle. And so therefore, we know it's a peritectic. And so once this composition heats above the peritectic temperature, we're going to form a liquid outside of the compatibility triangle, and that's what gives us the peritectic reaction. So this all happens at 1470. And so the first thing that's consumed in this case is calcium. So calcium is the first solid, now if we're looking at, apologies, let me go back real quick. So if we are cooling this down from a liquid, the first thing that forms is calcium, right? So calcium is the first solid that would be formed. So if we're looking at it from that point of view. So at 850 then, so if we continue down the crystallization path looking at the changing liquid composition, then we see that at this point, it reaches the boundary curve. So at 1850 is where we'd start to form a second solid phase, Ca3Si O5. So the 3,5 compound, I'll refer to it as. And so that's where we should get that form. And if we look at just before the boundary curve, we can also do the lever rule, binary lever rule, to determine that at that point we have 42% calcium oxide, 58% liquid from the lever rule. All right, so now brings us to the portion where we determine if we have partial resorption or not. And so we need to have one more sort of tool in our toolbox to be able to identify this partial resorption. And this is the alcomate line. So I've kind of put it as a definition up here. So what this is we're on a boundary curve. Therefore, we know we have equilibrium between two solids and a liquid. So in this case, we have lime or CaO, and then this calcium 3 silicon 1 oxygen 5 compound. So those are our two solids. And so they have compositions, those two solids, the primary phase fields, have compositions of CaO down here, and then the 3,1 component up here. So the 3 calcium 1 silicon dioxide is up here. So basically this alkymate line is the line joining those two compounds together. So this line that I've indicated in red is the alkymate line. And so what that's going to give us is we're going to compare this line to the boundary curve, and we're going to compare it to where we're at on this boundary curve. And I'll show you this in the next slide. Okay, so as we decrease the temperature and we're moving along this boundary curve, right, the liquid composition is continuing to change, we can see that we're sort of moving away from the two-phase region along this, and we're moving away from this alkymate line. All right, so the way we're going to use this to determine partial resorption is we're going to look at the progress we've made on the boundary curve. So let's take a look at the first portion we're at, right when we right where we intersect this boundary curve, so right where the arrow is pointing. What we're going to do is we're going to draw a tangent to the boundary curve. So you'll see that they have already done it here. So basically this solid line is tangent to the dashed line, which is our boundary curve. And we're going to draw it all the way back to this base of the triangle over here. And the important characteristic here is that we want to see where it is relative to the alkymate line. In this case, it intersects outside of the alkymate line. And this tells us that we aren't producing both solid phases, because if we were, our line would intersect in the middle of those two phases. So what that actually tells us is that during this portion of the curve, we actually have to consume one of the solids to get back to this within this alkymate line. So we want our tangent to be intersecting within the alkymate line for both of those to be produced. And so I've just kind of highlighted with the green dashed line here our tangent, and you can see it's outside of this alkymate line. And so what that means is that in this case, it's outside of the alkymate line on the opposite side of calcium oxide or lime. And so in this case, we actually are consuming calcium oxide along with the liquid when we're cooling this down to create this new solid Ca3SiO5. And then we're also forming a different liquid. So that happens because we're outside and we don't intersect the alkymate line. So this must be consumed or partially resorbed. And so again, if you're wondering why it's the calcium one, again, think of where we're at. Composition B is where we're forming calcium oxide in large amounts. And so to get kind of away from that composition, we have to sometimes consume some of that calcium oxide. All right, so we can look at this tangent along this whole boundary curve and see how it adjusts. So let's take another look at a different region. So let's say we're getting really close to this peritectic point down here. So we're further along, and so we're at this point with the blue dot. And so in this case, if I draw another tangent here, I can see that my tangent now is going to be different. And in fact, you can see up here that this tangent now is within this alkymate line represented by B. So this tells us that the calcium oxide no longer has to be consumed. And so in fact, it's the opposite. The liquid is going to calcium oxide, so we're producing calcium oxide again, and also the other solid phase and producing a different liquid. So that's what the tangent of the boundary curve tells us with relation to the alkymate line. It tells us whether something's being produced or consumed in these amounts. And so the other thing that we can get from this, is if I go back, the tangent, so whether it's within or without the alcomate line will tell us if we have something that needs to be consumed. But in the other instance, what this will tell us is it will tell us how much is being produced. So, in this case, we mentioned that both calcium oxide and this other calcium silicate are being both produced. So we can also use the relation between the tangent and this alcomate line to determine how much of each is being produced. So calcium oxide is over here. So if we use the opposite side of the alcomate line with the boundary of the tangent curve, so this little sliver right here, that tells us how much over the total length, tells us the amount of calcium oxide. And then this large portion tells us how much of this other calcium species that we're producing. So we can use that to determine the amounts of the relative amounts of these phase being produced. So this tells us there's a lot more calcium 3 SiO5 being produced than a small amount of calcium. So even though calcium isn't being consumed, we're not producing much in this area of the curve. And so we can use that all along this path to see how much is being produced or consumed in these cases. All right. Excuse me. So I have one last thing that I want us to do, and that is we have this new diagram. I haven't really showed this before. So what I want you to do is I want you to write the peritectic reaction that composition B will go through when it reaches 1470. So again, use the skills we talked about in the previous modules to see if you can come up with what is the peritectic reaction that goes through at the peritectic temperature. So pause the video, see if you can come up with that, and then we'll discuss in the next segment. All right, so this is where we're going to use those tie lines again to determine this reaction. And so I've highlighted the 4 phases involved here. We're going to have a liquid, calcium oxide, the Ca3SiO5, and then we're also going to have the Ca3Al2O6. So we're going to have these are our 4 phases that are going to be involved. Again, we can determine that from compatibility triangle plus the composition of the liquid. So, so this is the composition of the liquid at the peritectic point, and then the other 3. So this is the Ca3SiO5 is here. This is calcium oxide, and then this is the calcium aluminum phase over here. So those are our 4 points. Those are our 4 phases involved. And again, what we have to do is basically connect the lines in such a way that they will intersect. And so there's only one way in which that will happen, and that's if we join calcium oxide with the liquid and the silicon species with the aluminum species. And we join those species together. So that means, excuse me, that what will happen is liquid and calcium oxide will be consumed upon cooling to produce the silicon and the the aluminum species on the lower temperature. And so that's what ends up being our reaction here. And again, we can get this by creating these tie lines in this form and making sure that they intersect between those 2 in the middle. So this tells us that these 2 phases, the liquid and calcium, are consumed upon cooling, and these 2 are produced upon cooling. That's what those tell us. And again, we can get the relative amounts from the links that we have here, just like we did in the previous section.